Good morning, everyone. My name is Raj Patel from Aero section. Today, my topic is analysis of mode of interaction in ultra low frequency oscillation based on the trajectory eigenvalues. First of all, introduction. Ultra low frequency oscillation means ULFO has been observed in hydroelectric power system regularly in 2011, and oscillation with 0.05 to 0.08 Hz was observed in the Colombian power grid, and 63.8% generator are hydropower units. Similarly, low frequency oscillation means about of 0.05 Hz in China Southern Power Grid during analysis testing. ULFO has been detected and studied by mathematic models at the equilibrium points. Generally, the parabolic dynamics performance are attributed to turbine factors, electric device, electronic device, and uncertain loads such as a water hammer effect and poorly turned off controllers. Application scope of trajectory eigenvalues. The dynamic equation of power system can be defined capital X is equal to f of x y t, then 0 is equal to f of xy. The both are equation number 1, where x is the state vector, y is the algebraic vector, t is the time. Now, the nonlinear components of extended in Taylor series the first order terms. Decoupling components. With the time varying terms neglected by equation number 1, the range xt is equal to ak into xk plus bk. This is the equation number 1. Here, equation number 1 is a set of linear time invariant differential equation of which the solution can be analysis analysis that issued dxk is equal to uk dt ck dt into ek dt minus uk0 ck0 and ek0, where uk and ck are the model matrix and intermediate matrix. Here there is a decom solution of decoupling components. Dxt plus delta xk delta t by d of tk plus delta t is equal to f of tk into y by dk plus sigma f by uh, dou f by dou x delta xk delta t plus this is equation number 2. Here dou f by dou x is equal to non Jacobian matrix. Dou f by dou x form y factor partial derivative matrix. So delta x into delta t is equal to ak into delta xk plus delta fk delta t plus bx. This is equation number 3. Here the eigenvalues of ak can be denoted by the expression of the above matrix and vector can be found in A. So x is equal to uk ck v ek t minus tk. This is equation number 3, where small t is equal to tk plus delta t. Now we substitute. So x new k minus x new k tk is equal to delta xk delta t. So we make a one matrix. So ak is equal to uk inverse ak into qk. So here equation number 9 is the time varying characteristic of the first eigenmodes. Eigenmodes matching based on transfer matrix. The eigenvalues of a matrix continuously change with the perpendicular of the parameters of the matrix. The detailed description of the theorem is listed in appendix B. As a result, the transfer matrix tends to be identified matrix with the discrete steps size of integration. In other words, A time section with VD3 can be disappointed into a series of the time section with VD1 and VD2. The value distribution of the transfer matrix approach VD1 when the step size is a discrete. Theoretical, the result of eigenmodes matching can be improved by discrete signs. Matching criteria. So creation 1. Criterion 1. Uh, Criterion 1 is used to the approximately of TK to an identity matrix of which the determinant of equation equal to 1, considering that determine the reflex in all elements of TK, those sections with all alignment eigenmodes satisfying VD1 can be identified by the strict criterion 1 with a smaller value of 1. Then uh, d d into tk into d power t is equal to t. So a dash k is equal to da into d power t. Creation 2. A large sum of simulation tests exhibit that the amount of the time varying eigenmodes is usually finite, while the order eigenmodes satisfy of VD1 in order to match the eigenmodes at a TK creation 2 is applied to the eigenmodes with the potential. Coordinate matching criteria. Here the chart is a coordination of matching criteria chart. Obtain of dt d power t is equal to I. Here I is equal to 100,011,001. We are already discussed about previous slides. Now start of T of K is equal to Tk is equal to V2 Ux and the end of deliver A dash K into Dk. There are calculation of previous slides. Tk is obtained by multiple Vy and Ux. Creation preference identify the type distribution of Tk repeatedly. Here delta K is equal to max the lambda k I minus lambda k minus 1 I divided by max I equal to 1 to n mod of lambda ki into 10 raised 10 power minus 6. So lambda ki infinite substitute lambda k a and lambda k minus 1 is a lambda k minus 1 b. Mode interaction in ULFO. In case information of a special phenomena are observed in two mechanical test systems with the structure shown in figure. Structure of machine test system. This is a structure of a two machines as test system. Turbine with a governor. The classical mode is used to represent a two generator. G1 is a water turbine equipped with a generator, whereas G2 is a steam turbine. This is a G1 turbine and a steam turbine. G2 is equal to steam turbine. The dynamic equation are listened to approx of the line data, generator data, and governor data are listed in approximation E. The eigenvalues are equilibrium point and the nonlinear index of the normal form techniques are obtained in table. So this is a nomenclature, real parts, imaginary parts, EMCR, lambda 1 real parts minus 16.0361, imaginary, imaginary part plus 0.000I, lambda 2 real part minus 0.1145 and imaginary part plus 3.5487i. So eigenvalues at the equilibrium point in the test system table. A couple of imaginary roots and two real roots, lambda 4 and lambda 8, are produced by hydroelectric power governed. As seen in the table, the positive values lambda 5, lambda 6 contribute the negative dumping. So the lambda 5, lambda 6 is the negative dumping values at the equilibrium point. The lowest frequency is the lower than zero point 0.1 Hz as reach of 0.08 Hz in the non-electromechanical nodes of lambda 5 and lambda 6. The order eigenmodes lambda 2 and lambda 3 refer of electromechanical oscillation frequency of 0.56 Hz. The dumping lambda 5 and lambda 6 are positive, which means these eigenmodes are negative dumping. So here COI of rotor angles, this is a timing 50 second, 100, 50 second, 100 second, 150. Here components of signal composition. First one is a trajectory of components. Second one is a trajectory components too. Here frequency is the here there are six graph A, B, C, D, E, F. So the graph is described about of frequency lambda 2 or lambda 3. When lambda 2 and lambda 3 value increase, decrease. Here C and D graph is observe lambda 5 or lambda 6 when one time of lambda 5 and lambda 6 value is a constant to 0 minus 0.1 to 0 and one time 0 to 0.1. The trajectory where lambda 5 and lambda 6 vary with the time period where as a lambda 8 keep the straight line parallel with the horizontal axis during 0 to 50 seconds and regularly jump in the rest of the curve with the respective moments of the operating point between the dynamical center at the first endpoint. The dynamic characteristic lambda 5 and lambda 6 fall somewhere between two poles of negative dumping acceleration, exponential trends. It's a growth of change of lambda 2, lambda 3, and lambda 5, lambda 6 are always smooth. With the operating points of deviation equilibrium points, the characteristics of eigenvalues, eigenmodes become of the differential table first. From the above discussion, it is a clear of dumping characteristic lambda 2, lambda 3, and lambda 5, lambda 6, lambda 8. Here, lambda 2, lambda 3, we are already discussed about previous slide graphs. So, one time of lambda 2 and lambda 3 values is decrease, increase. That's it. Thank you.